Hi, I'm Jaeha Kim with Seoul National University, and today I'll present a UVM Reactive Testbench for jitter tolerance measurement of high-speed wireline receivers. Jitter tolerance test measures the resilience of a high-speed wireline receiver. It applies a sinusoidal jitter to the transmitted data and raises its magnitude until the receiver can no longer satisfy the target bit error rate. This plot of the largest tolerable magnitude versus frequency of the sinusoidal jitter characterizes the jitter tolerance of the receiver. This work presents a UVM test bench for measuring the jitter tolerance. To do so, the test bench must be able to simulate analog circuits in SystemVerilog and perform an iterative search, finding the largest sinusoidal jitter magnitude in a small number of trials. As you know, Universal Verification Methodology, or UVM, is a library of components for building reusable test benches for digital systems. Surprisingly, you can use the same UVM components for analog and mixed signal circuits if you use a well-defined fixture module satisfying these two requirements. First, it must enclose the device under verification modeled in SystemVerilog. Second, it must enclose the instrumentations for generating stimuli and measuring responses as well, so that no analog waveforms need to be processed outside the fixture module. However, a high-speed wireline transceiver is a large, complex system, including many analog mixed signal circuits, such as this transmitter, transmission line channel, receiver, equalizer, this clock generating PLL, and clock and data recovery circuit. To model this system and estimate its BER, we must be able to simulate analog pulses propagating through the lossy channel, express precise timing of the clocks produced by the PLL and CDR, and model the circuits directly as a network of circuit elements in SystemVerilog. This work uses XMODEL to meet these requirements. XMODEL is a plugin extension developed by Scientific Analog, enabling fast and accurate analog mixed signal simulation in SystemVerilog. XMODEL uses a unique event-driven algorithm enabling fast simulation speed. It can support both functional and circuit-level models of analog circuits, and it is fully compliant with SystemVerilog-based flows such as UVM. The event-driven algorithm of XMODEL is ideal for simulating the data pulses propagating through the lossy channel and equalizer. The waveforms on this slide illustrate that XMODEL is capable of simulating accurate analog waveforms while triggering the events only when the input has events. This makes XMODEL much faster than real number model, which has to trigger far more events to achieve the same level of accuracy. Composing model with XMODEL is basically putting together the building blocks called XMODEL primitives. And because of that, we can show its model either in this schematic form or in this source form. Some primitives represent the circuit function like these D flip-flop and transition primitives, while some others represent the circuit elements as is like these NMOSFET, register, and iSource primitives. XMODEL introduces two new data types, XReal and XBit. XReal is for describing analog circuits in an event-driven format, and XBit is for timing accurate digital signals. That is, the timing resolution of the XBit signals is not limited by the time step of the SystemVerilog simulator, making it suitable for simulating jitter-sensitive data and clock signals. The Fixture module also needs to include analog instrumentations that can generate stimuli and measure responses. For our case, we need a way to generate a clock with the prescribed SJ frequency and magnitude, and also need a way to measure the BER of the received data. Again, we can do these using the XMODEL primitives. Particularly, XMODEL is capable of performing efficient statistical simulation, which can estimate the BER as low as 10 to the minus 12 with only 30,000 bit samples. With this Fixture module enclosing the high-speed receiver model and its instrumentation, described with XMODEL primitives, we can now build the rest of the test bench using the standard UVM components. Namely, we will take a look at the sequencer component, driver component, and the scoreboard component that can collectively measure the jitter tolerance of this high-speed receiver model. To perform an iterative search, finding the largest SJ magnitude meeting the target BER, we need a way to choose the next magnitude to try based on the BER results with the previous magnitude. Cliff Cummings et al. Presented a method called reactive stimulus technique to do just that within UVM. The key difference with the ordinary sequence and driver component is that the driver can now talk back to the sequence. When the driver returns the response with the item done method, the sequence can grab that using the getResponse method. Then, based on the result values contained in the response, the sequence component can choose the next item to try. Using this reactive stimulus technique, the sequence component performs the search in two steps. First, it uses a linear search algorithm to identify an interval containing the BER pass and fail boundary. Second, it performs a binary search within that interval to refine the boundary location, that is the largest SJ magnitude meeting the target BER. When the driver initiates a new trial and retrieves its results, it also broadcasts that results to the scoreboard. The scoreboard keeps the record of the maximum SJ magnitude meeting the target BER for each SJ frequency. That is, when all the search is over, the scoreboard will have the jitter tolerance characteristics of the high-speed receiver under verification. For UVM simulation measuring the jitter tolerance at 20 SJ frequencies, the test bench ran a total of 106 trials, which took about 41 minutes in total. This is the simulation log listing each trial and its results. When the simulation is over, the scoreboard reports the collected jitter tolerance characteristics in a table format. You can also plot the SJ magnitude versus SJ frequency graph, which visualizes the timing margin and tracking bandwidth of the high-speed wireline receiver. I hope you're now convinced that a UVM test bench for an AMS circuit requires nothing but a well-defined fixture module. For the rest, you can keep using the standard UVM components. For this example of measuring the jitter tolerance of a high-speed receiver, we built a Fixture module enclosing the Transceiver model and its instrumentation using the XMODEL primitives. And we performed the search for the maximum SJ using the reactive stimulus technique. Finally, I'd like to acknowledge that this work was supported by Samsung Electronics, and the EDA tools were supported by IDEC and Scientific Analog. Thank you.